Howdy, if you're joining me, I am Victoria Schmidt with the T Smart Grid Center. We'll be starting in about 3 minutes. Howdy, I'm Victoria from the T's Smart Grid Center, and I'd like to thank you for joining us today for the Smart Grid Center webinar, all about power flow alternative solutions, including how to avoid them. If you have any questions during today's presentation, please send them via the Q&A feature at any time. We'll do our best to answer as many questions as possible at the end of the presentation. Today's presenter is Dr. Thomas Overbye, who is the director of the Smart Grid Center, holder of the O'Donnell Foundation Chair 3 professorship in the Department of Electrical and Computer Engineering at Texas A&M University, and Section 6 chair of the U.S. National Academy of Engineering. Prior to joining A&M in 2017, he was a professor at the University of Illinois at Urbana-Champaign. Before starting his academic career, Dr. Overbye worked as an operations engineer for Madison Gas and Electric. He is the original developer of Power World Simulator, the co-founder of Power World Corporation, and has extensive experience in many aspects of electric power systems, including participating in and leading numerous large-scale electric grid studies. Moreover, Dr. Overbye is a passionate educator, co-author of a widely used power system analysis and design textbook, and has received numerous awards for research and teaching from both academic institutions and the IEEE Power and Energy Society. Dr. Overbye, take it away.
Okay, thank you, Victoria. And as Victoria mentioned, today I'm going to talk to you about power flow alternative solutions. The power flow, and I should say that these slides are available on my website. I've included the link down there, so if you don't catch something in the slides, you can download them there. So the focus here is on power flow solutions. Of course, power flow is a widely used power system analysis technique, and it can have multiple solutions when it's in its standard AC positive sequence form. So the goal here is to try to find the right solution, and usually there's just one solution that we're going to call the operable solution, and in the slides I'll call it OPRS, and to avoid the other solutions, which we're going to call the alternative solutions. Before I get into the presentation, I did just want to give a quick advertisement for some of our upcoming short courses here at Texas A&M, including one next week. The one next week is called the Primer on the Planning and Operation of Large-Scale Electric Grids. The target audience for that is non-technicals working in the power area. So if you're participating in this webinar, you're probably not a non-technical working in the power area. But if you know someone who is, feel free to pass on the information. We do have a short course focused on the fundamentals of transmission planning, which is a great course for new power engineers or anyone who would like to learn more about transmission planning. And that does have more of a technical focus. And then one course that we're super excited about is the application of artificial intelligence in power systems. Jonathan Snodgrass is going to be running that one. And given how much AI is in the news, it's of course certainly impacting our industry. And Jonathan has put together a great course. So I think a lot of people here will find it useful. So we hope y'all can join us. The courses are at our Smart Grid Lab facility at the Texas A&M Rellis campus in Bryan, Texas. Okay, so into the presentation. The gist of what I'm going to tell you is, yes, power flows have these alternative solutions, and usually you don't want them. And there's a couple ways that you can avoid the alternative solutions. Some of this involves taking advantage of options that are in the power flow solution themselves, and I'll talk about some of those at the end of the presentation. As much as possible, you want to avoid large power change or large changes in your power flow when you go to solve, so I mean, certainly some changes are going to occur, but the larger changes increase the likelihood of the algorithm converging to an alternative solution. One that is a relatively easy fix is if you enter new buses into a power flow. A lot of times the software, and Power World Simulator certainly does this, is it will internally set the angle to be a good value. But if you explicitly tell it an angle, and a lot of times that's a flat start angle where it's 0 degrees, that might actually lead to convergence to an alternative solution. And then we'll finish up on some new software that we've developed to help people explicitly model the wide delta phase shifts that are increasingly included in the power flow. Okay, so alternative solutions in practice. The bottom line is I don't know how often these solutions occur, and I don't know that a lot of people know how often they occur, because you can get an alternative power flow solution and you may not know it. And this is an example of a case. This was actually associated with the August 14, 2003 blackout, in which the power flow had solved to an alternative solution and had been at an alternative solution for months, and people just didn't know it. Part of the reason why they didn't know it was because it was not affecting the footprint of interest, but it was still affecting the solution values. So the alternative solution here is shown in the areas in red where there were quite low voltages. So these things do occur. In a large case, you can easily get an alternative solution, and you may not know it. Okay, so before I go further, I did want to just clarify the terminology that I'll be using. If you work in this area, you know that as power engineers, some of us will say the term power flow and some of us will say the term load flow, and we mean the exact same thing. I prefer the term power flow because I think it's the powers that flow, not the loads, but load flow is certainly common as well. And as I researched this, the two terms have been used interchangeably in our industry for more than 65 years. So if you look at papers from the 50s, some people are saying power flow and some are saying load flow. So today I'll be using the term power flow. Modeling cautions. When we model any engineering system, we have to keep in mind that our models are not a true representation of reality. They're just an approximation to reality. This is one of my famous technical quotes by George Box, who was a professor of statistics at my alma mater, University of Wisconsin-Madison. So when we model the power flow, the power system, and solve it with the power flow, we're making an approximation. And those models, if you push them too far, they will fail. And when we go into alternative power flow solutions, they will certainly fail. So Box went on to say the practical question is how wrong do your models have to be before they are no longer useful. Okay, we're going to be talking about nonlinear systems today. The power flow in its standard AC form is a nonlinear solution method. Linear systems are nice. Linear systems have the principle that the output is proportional to the input, and you can apply superposition to them. If you work in market analysis, you might be solving DC power flows. DC power flows have the very nice property that we are solving a linear system. And when you solve a linear system, you only have one solution. And as long as your A matrix is invertible, you're guaranteed that a solution exists. This is not the case with nonlinear problems, and the standard AC power flow is definitely nonlinear. Okay, so in a linear circuit, this is a slide that just gives a simple DC circuit where I've got two batteries, three resistors. That's a linear circuit, and you can solve it with the principle of superposition. When we teach this in a circuits class, that's oftentimes how we do it. If I take that central resistor, R3, and replace it by a constant power load, then suddenly I've changed my linear system into a nonlinear system, and I can actually have either no solution depending on the magnitude of the power that I'm trying to supply there, or I might have multiple solutions. To give you a simple example of this, let's say I've got a 9-volt battery and I've got 1 ohm of internal resistance in the battery, and I want to supply a load that is consuming 18 watts, and say it's a resistive load. There's actually two solutions to this relatively simple problem. One solution is the load is 2 ohms, which means we have 3 ohms of total resistance. So we got 3 amps squared times 2 is 18 watts. Another alternative is the load is a half ohm, then we'd have 6 amps of current, and again, we'd have 36 squared times 0.5, so we'd have 18 watts. In both cases, we're supplying 18 watts, but they're quite different solutions. If I said the load was 0 power, then one solution would be an open circuit and another solution would be a short circuit. So this sort of multiple solutions is inherent to modeling constant power loads, and in the power flow, we're going to have constant power output of generators. So there's no getting around this. The question is, how do we best manage it? Okay, so this is the power flow equations. Either you know these equations or you don't. But you look at that, you can clearly see that we've got nonlinear terms there. We've got values that are squared, and we've got sines and cosines. So we are solving a nonlinear problem. This problem can actually be formulated when the voltage, with the voltage represented in polar form, which is what I'm doing here, or you can formulate it with the voltage represented in rectangular form, where you say the complex phasor voltage in rectangular form would be VI is equal to EI plus JF. They will give you the same solution, but how they get to the solution, if you model a power flow with the polar form of the equations versus the rectangular form, they will take a different solution path, and one of those paths may not lead to the operable solution, or actually both of them might not. Okay. The slack bus, of course, if you solve a power flow, you can't. Power flow is a static analysis technique, so that you can't specify the total generation, or you have to add a bus in to make sure that the total generation is equal to the total load plus the total losses. We also need an angle reference bus, so this is what we call the slack bus. Okay. Newton-Raphson algorithm. Most people are pretty familiar with this. There I've given it in scalar form. Just as we pick an initial guess, and this initial guess is going to be very important in determining what solution we converge to, and then we iterate and get new values of x that are hopefully closer to the desired solution, and we keep going until our mismatch is below some tolerance. So here we've got a slide where I'm solving x squared minus 2. I've graphed it out there, and you can see from the graph, and of course you know this as well, that equation has two solutions. It's got one solution that is at square root of 2, and it's got another solution that is minus square root of 2. Which solution I converge to with the Newton-Raphson algorithm depends upon your initial guess. So we're going to use the terminology region of attraction, ROA, to denote the set of initial guesses that converge to a particular solution. And what we will be trying to do is to make sure that our initial guesses are in the ROA for the desired, or what we're calling the operable solution for the power flow. Okay, so this is a power flow formulation in polar form. We're solving for the angles at the buses and the voltage magnitudes at the buses. Sometimes, of course, the voltage magnitudes are fixed because you've got a PV bus, and your set of equation is the power balance equations. Real power balance and reactive power balance at the non-PV buses. And at the PV buses, oftentimes we just replace the Q equation by an equation that says the voltage magnitude is equal to the set value. There's the Newton algorithm, which is very simple to present. When I started teaching power systems back in 91, I taught the undergrad power systems class at University of Illinois. Mark Laufenberg, who's the Power World president, was actually a student in my very first power system analysis class. And I taught a similar class last semester here at Texas A&M. This semester, I'm teaching a graduate level class that is covering power flow, but at a little bit more advanced level. The basic algorithm is given there, and we used to have students code this up when we taught it. Now, rather than coding it up, we have them do a design project, which I think is more pertinent to where most of them are going to go with their careers. But if you do commercial software development, power flow development, you know that much of the vast majority of what goes on in a commercial power flow is dealing with the complexities that are added to these relatively simple equations. And those complexities include managing the voltage and reactive powers, and managing area real power interchanges. And how these are managed can have a major impact on whether our algorithm converges to the desired solution or an alternative solution. Okay, so here's a simple example, two-bus power flow. I've got two unknowns. I've got a slack bus on the left side. I've got a constant power load bus on the right side. My two unknowns are theta 2 and V2. I can formulate it as a set of, it'll just have two equations, a set of equations where I've got the magnitude of the voltage and the phase angle, and then the 2 is the constant real power. I guess the 2 is right there. In the reactive power equation, which is right here, the 1 is the constant. This is the constant real power. That's the constant reactive power. I could also formulate it as a rectangular form. And here I've got EI and EJ. And of course, I would just have, again, two unknowns. I'd have E2 at E2 and F2. Okay. So if I solve it, I get a nice power flow solution. The per unit voltage is a little low, 0.85 per unit, but not too bad. I've got my generator producing reactive power and things are pretty good. But if I change my initial guess and I guess not a flat start value, a flat start would be 1 at an angle of 0, but I guess say voltage of 0.25 at an angle 0, those same equations converge, but they converge to this solution here. Again, I'm supplying 200 megawatts and 100 megabars to load, but now the voltage at the load is 0.26, and I've got a generator supplying way too much reactive power. Some people call these low voltage solutions. I started using that term when I was in grad school because the voltages I was seeing were low. But since then, I've seen a lot of examples where the voltages are not low. So the term alternative solution is a better one to use. Associated with this, we have something called PV and QV curves. PV curve is a curve where you plot on the y-axis the voltage magnitude of your solution, and then on the x-axis you plot a p-value. It might be the p-value at a particular bus, or it might be the p-value at a set of buses. And you can have a set of high voltage solutions and you can have a set of low voltage solutions. And since this has a shape that sort of looks like a nose, people often call these the nose curves. You can do the same thing with reactive power, plot the voltage magnitudes, increase the reactive power. Sometimes it looks very similar to the PV curve, of course, with modified units. But sometimes these curves do not look anything like, well, I mean, they have a rough shape as the other curve, but here the voltage levels are not particularly low. This is an example that one of my students did with a power flow that we were using to do geomagnetic disturbance analysis, and we were seeing the voltage fall off, but we'd see a low voltage or alternative solution where the voltage was also falling off, and then it was meeting what we call the bifurcation point at a relatively high voltage. So just because you've got an alternative solution does not mean the voltage magnitudes are low. Oftentimes they are, but that's not true in general. Okay, so what you can do is you can, if you're into kind of understanding how the initial guesses impact the convergence, you can create 2D plots of the region of attraction. Some people call it the domain of attraction. Here we did it where the positive values indicate the number of iterations it took to reach the operable solution. And then for different guesses, and here we're parameterizing the space as the initial guesses, the x-axis is the voltage magnitude of the guess, the y-axis or the voltage angle of the guess in degrees, and the y-axis is the per unit value. Initial guess of 1 at an angle 0 would be right here within the operable solutions region of attraction. The purple ones are the initial guesses that converge to, in this case, it's a 2-bus, so it's got a single alternative solution, which is down here. Of course, it takes positive iterations to do that. We're just using the convention that if it converged to the alternative solution, we would assume we take the flip sign of the iteration, so the plot would have a negative value there. Okay, so the goal in doing a power flow, whether it's a 2-bus or a 20,000 bus, is to make sure that your starting point is in the orange region. What the behavior of this region is, its shape depends on the algorithm that you use. Here, on the left side, we're using a polar form on the Newton-Raphson, and it gives kind of this complex shape. If you switch over to using a rectangular formulation, and when you use the rectangular formulation, There's a technique called the optimal multiplier approach that we do use in Power World. It comes from a paper from 1981 that allows you to prevent divergence, and the optimal multiplier does give us smoother boundaries. Although, as you can see, the uh, region, the area of the ROA for the operable solution really did not change that much. In fact, it might actually be higher on the left side than on the right side. We recently did a paper that has been accepted for the North American Power Symposium, where we were looking at the region of attraction for not just the two bus cases, but for much larger systems as well. One of the images from that paper is we were looking at the region of attraction for a 42 bus case. And here we would take a particular bus. Now, when you go beyond two buses, of course, your region of attraction has a dimensionality that is equal to 2 times the number of slack buses. So it's a very high dimensionality. But in order to produce a graphic, you have to just kind of project that into a 2D space. Here we were projecting into a 2D space where we were keeping the operable solution values at all the buses except for one bus, bus 34, which is up here. And the point of this was to say, one is the region of attraction for the operable solution in this case is pretty narrow, is not a large region. And the other is that if you look at a flat start value, which would be 1 at an angle 0, the uh, operable solutions ROA does not contain that point. So if you do a standard flat start guess here, starting with the other solution values, you would not converge to the desired solution. You'd actually converge to an alternative solution. Um, we wanted to look at projections in other domains. I mean, other projections rather than just voltage, magnitude, and angle at a single bus. So we took a 3-bus case and we did the variation of the voltage magnitude at bus 2 and the voltage angle the voltage magnitude at bus 2 and the voltage magnitude at bus 3. We then ran, in order to get the resolution higher on this image, we ran quite a few power flows. We actually ran more than 2 million power flows to produce this image here. Again, it's a projection of the ROA now for just a 3-bus system, but now we are getting 4 solutions. We get a solution that is our operable solution, the desired one, and nicely, it's got a very large region of attraction. There's a second solution, a third solution, and a fourth solution here. And you can see that their boundaries are quite complex for the region of attraction. Here's one where we did I think it was a 37 or 42 bus case. We were looking at the phase angle. There's a phase shifter down here, and we set the phase shifter equal to a pretty large angle value, but it was no larger than angle values that we encounter in commercial power flow cases. And then we did the same analysis where we were varying the voltage magnitude at one side of the phase shifter, and at the other side of the phase shifter, we were also varying, we weren't varying the voltage magnitude, we were varying the voltage angle on one side or the other side, keeping all of the other values at their flat start solution, and then plotting out which angle guesses got us to the operable solution. The operable solution here is again in red. With this example, we again had 4 solutions. Like before, the initial flat start 0, 0 is not in the ROA for the red solution. It's close, but it will not converge. It will diverge. We also did quite a few solutions to get this image. Originally, we ran the image at a low resolution. And then I was talking to Sanjana, who's a grad student working in this area, and I said, Sanjana, we have to get a higher resolution image. So we decided to run a large amount, and it's kind of cool. It almost looks like kind of abstract art there. A little bit of history on alternative power flow solutions. They go way back. If you look at some of the early papers, the first mention of alternative solutions in English is, I believe, a 1972 paper from the Power Systems Computational Conference. Uh, it's a great conference. I've been to it a number of times. Uh, the first mention was in 1972, although if you look at that paper, they're actually referring to earlier papers that are in Russian. Another paper 3 years later shows the image here that clearly indicates that the power flow has multiple solutions. So this is not a new uh, finding. We've known this for more than 50 years. Um, when I started grad school, I worked for Madison Gas and Electric, so I was interested in power flow solutions. And I also early on in my grad career, I read a book by James Gleick, it's called Chaos: The Making of a New Science. And in that book, I learned about fractals, and I learned that regions of attraction could be fractal. And he gives an image in his book of x cubed minus one and shows the region of attraction for that simple system is fractal. So I was wondering in my early grad student days, is a region of attraction fractal for the power flow? And it turned out that we were getting things that started looking like fractals. So this is a image from my first paper, which I wrote with my PhD advisor, Chris DeMarco, from 1988. I was just doing this on an 8088 computer, and I had a dot matrix printer, so I couldn't do too cool of images. Jim Thorpe, who was a professor at Cornell at the time and later at Virginia Tech, he had access to supercomputers. So he kind of took this work and extended it quite a bit and produced some really cool images. A very nice paper is one that he authored from January 1997 called Load Flow Fractals Draw Clues to Erratic Behavior. The paper is published in color, I've seen it in color, but I could not find that image in color. But the image that he had in the paper here looks very similar to the images that we showed for the three bus case. So again, what we're doing with the three bus case is not new. The focus, of course, is not to make pretty images, fun as that may be, but rather to increase the region of attraction for the desired solution. Okay, when we talk about alternative solutions, people always say, well, how many of these things exist? The short answer is there are lots of them. A little bit more extensive answer is it depends on the system loading, which it certainly does. If you take an unloaded system and you think that if it's unloaded, the load at each bus is zero, and at each bus, you can achieve zero loading by either an open circuit condition or a short circuit condition. And if you say, hey, I can do combinations of that at all the buses, that means that you could potentially have 2 to the n power flow solutions where n is the number of buses. Now, as the system gets loaded, all these solutions do not exist, but there are lots of solutions that exist. And some of my early work in this area, I was looking just at a three bus case, and we saw this in the earlier example, is you can have 4 solutions. And as you increase the loading on the system, what happens is 2 of those solutions will bifurcate, they'll join together, coalesce here. And then you go from having 4 to 2, and eventually if you increase the loading high enough, the remaining alternative solution coalesces with the operable solution, and then you have a case where there's no solutions. When we talk about power flow and alternative solutions, it's very common to hear people use the terminology SCP and UEP associated with these solutions. SCP stands for stable equilibrium point, and UEP stands for unstable equilibrium point. Um, when you talk about stability, you kind of have to assume dynamics. Power flow is a static analysis tool, so it does not have dynamics in it. So you really can't talk about the stability of a power flow solution. But if you say, I've got standard power system dynamics, then that solution, if it's the operable solution, it will have if the dynamics are stable, the operable solution can be called a stable equilibrium point. Turns out that the alternative solutions end up giving you an unstable dynamic response if you assume standard power flow dynamic or power system dynamics. So we will sometimes hear the term UEPs for these alternative solutions. There's a nice paper. Jim Thorpe appears there again. Jim Thorpe unfortunately passed away a number of years ago, but he did great work, and he was always fun to talk with and learn from. He showed in 1989 the relationship between these alternative solutions and the stability of the system. One thing he showed that is you can classify these alternative solutions based on how many positive eigenvalues they'll have in the Jacobian of the power flow, and a type 1 UEP would have a single positive eigenvalue. Okay. Do we ever want these solutions? Usually you don't want these solutions, so people don't want them. There are some exceptions that exist, and one of the exceptions that existed was actually my work that I did on voltage stability using energy methods. So I spent a lot of time in my grad career or early faculty career actually looking for alternative solutions because we would use them to assess the voltage stability of the system. So there are some applications, but they're not widely used, and most people don't want these solutions. Okay, one of the issues that you run into when you're solving a power flow on a large system is you can get substantial angle variation across the system. And this is a contour of the angles in a 23,000 bus synthetic grid that we developed over a footprint here in the mid part of the US. And you can see that the angle variation ranges from 150 degrees to minus 150 degrees. So if you make an initial guess, like let's say you add a new bus to this system and you make a guess saying, well, I'm just going to set its angle to 0, chances are that initial guess is not going to be in the region of attraction for the alternative or for the desired, the operable solution. We actually in this NAPS paper, we took that 23,000 bus case and we did initial guesses at all 23,000 buses in the case and looked to see which ones converged to the operable solution. Turned out that only about 37 or 38% of the initial guesses converged to the desired solution. The other ones converged to an alternative. Almost all the other ones converged to an alternative solution. We then looked at a particular location. Here we picked a location in Michigan, and we could have run the 2D analysis to get the ROA and put out a nice graph. That's a lot of powerful solutions, and it was a 23,000 bus case. So we figured, look, if you're making an initial guess of a bus voltage, magnitude and angle, chances are you're not going to guess a low voltage. If you're looking for the desired solution, you just guess one or something close to 1. So we just did an angle sweep where we swept in a 1D sense all the initial guesses where the magnitude was 1, and then we changed the angle between minus 180 and plus 180 for this bus in Michigan that had a operable solution of minus 116 degrees. The region of attraction was centered about that. It was about, you can see the range of it there is about 30 degrees on either side. And other ones, including the flat start one, were outside of the region of attraction. So again, a takeaway message is if you're making an initial guess, maybe you're putting it into a script that you're loading up, try to guess the angle that is close to the angles of the buses that are going to be neighbors to the new one. Detecting alternative solutions. A quick way to detect alternative solutions is to look for low voltage. Certainly, if you start seeing voltages below, 0.6, 0.7 per unit, that's going to tend to indicate an alternative solution. The nice thing about this is it's very quick to sort the bus voltage magnitudes and look. The difficulty, though, is it can miss some. So there are more comprehensive algorithms. These more comprehensive algorithms work by looking at the sensitivity of the voltage at a bus to a reactive power injection at the bus, what we call the dVi, dQi values. If these are negative, to identify locations in which these values are negative. The only caveat is that won't be true if you've got negative reactance branches. Negative reactive branches in a power flow are actually quite common. They occur because of series capacitors, which are not common, but they also occur on some of the branches of the three-winding transformer equivalent circuits, which can be very common. The nice thing about this approach is if you use sparse vector methods, which have computational order of about log n, hence you can check all of these values with computational order n log n, which is similar to what you get in a quicksort. So it's relatively straightforward to check all of them. As an example, on that 23,000 bus case, we're using Power World Simulator, and if you go to one of the sensitivity pages, which I've given there, just check to calculate the dV/dQ values for the diagonals, calculate the sensitivities. It will tell you which buses in the case are associated with alternative solutions. Of course, a power flow will have an alternative solution when you're analyzing it, but you can kind of narrow down where's kind of like ground zero for that alternative solution by looking at these sensitivity values. And that's what this form does. So I'd encourage people to do this sort of analysis, at least occasionally on your power flows. How do you avoid these things? I went through these at the beginning, but I want to reiterate them here. One thing you want to do is if you do get an alternative solution, you do want to know it because it can persist. If you solved an alternative solution, like the early example indicated, it might be in a part of the system that you don't care about. If you don't care about it, maybe it's not really affecting your results, but it would be nice to know if it's there. And then, then you could, uh, you'd have to start with a different solution to get away from it, because once you get to an alternative solution, they don't tend to resolve themselves. One of the research areas that we're working on is to take a power flow that's converged to an alternative solution and then kind of get it to go back to the operable solution. So we are working on that. I hope to have some results on that shortly. One way, which I've covered already, is the algorithm you use. The polar algorithm converges differently than the rectangular algorithm. So if you took a power flow and it converged to an alternative solution, you might want to change the Newton-Raphson algorithm that you're using. Will it always solve the problem? No, they both might converge to alternative solutions. If you're using the rectangular with the optimal multiplier, the good thing is it probably won't diverge. Polar might diverge, but you might luck out and one might converge to the alternate or to the desired solution. Another option which different power flow packages have, including Power World, is that a constant power load cannot persist as the voltage goes down to zero. So what we do is we provide an option where as the voltage goes down, and once it goes below a tolerance value, a constant power load, and here's the normalized load as the voltage is falling, eventually converts into a constant impedance load. And this uh, it doesn't necessarily prevent you from solving to an alternative solution, but because with this curve, the alternative solution is going to have a value of zero power at zero voltage, it will oftentimes drive that alternative solution down to 0 volts, which is a short circuit condition, which makes it very easy to at least see that it's occurring. So that's one option. Another option that we are just exploring is when you make a bad initial guess, a lot of times you get high mismatches associated with that initial guess. And we can look at the mismatches on the branches coming into locations where the initial guess might be bad. If those flows are much above the rated limits for the transmission line, chances are there's something wrong with the initial guess and it may cause an alternative solution convergence. So we've got now, this is newer in Power World, where we've got an option that you can look at the branch limit scalar, and if it's below a rating of the limit, or I'm sorry, if it's above a rating of the limit, we will modify the initial guess to um, make it something better. Now, one of the challenges in adding these options for changing the convergence patterns of the Newton-Raphson algorithm is we want to do no harm. And we want to make sure that we don't add a new option and set a default value that people are suddenly having power flows that were working and they're no longer working. So there's kind of a balancing act here. We don't want to make the checking of the alternative solutions so aggressive that it messes up, and it could mess it up by taking a long time to converge. That would be a potential likely outcome. So we're doing some research on looking at the impact of these options on convergence. One thing, and with this I'll finish up, is when you model a positive sequence power flow, of course, in the power system, there are delta Y connected transformers, and these delta Y connected transformers have 30-degree phase shifts associated with them. In a positive sequence model, you do not need to include those phase shifts. The phase shifts are multiples of 30 degrees. What we are finding, though, is increasingly people are including these phase shifts in the power flow, and that does not change the solution. It just shifts the angles. But the caveat is it can be trickier to converge if you shifted the angles by putting in 30-degree, or if you're putting in 30-degree phase shifts and then want to use a standard flat start solution, that's not going to work. So Power World has recently introduced a new data type called phase shift groups. And the idea of a phase shift group is to just find the subsets of the power system, subnetworks, in which the angles in that subnetwork are all shifted because of these 30-degree phase shifts that, again, they don't need to be modeled, but they are increasingly modeled. A simple example is you might have a generator connected through a generator step-up transformer, GSU, where you've got a grounded wire on the high side and delta on the low side. That's going to induce a 30-degree phase shift. Maybe to represent that in the power flow, you include a minus 30 degrees on the transformer. That's fine, but it's good to know that is going on so that if we want to do a flat start, or if we want to set the angle for a new bus that you're adding by that generator, we know it. So this is where the phase shift groups come in. This is a simple example. I took that two-bus system, added a step-down transformer for a load, modeled a 30-degree phase shift on it. Again, whether I put that 30-degree phase shift in or not in the power flow does not affect the power flows. It affects the angles. Here you can see the angle is shifted by 30 degrees, but it's not going to affect the voltage magnitude. Okay. Here's an example where I took a recent WECC case, 27,000 buses. I took PowerWorld's new tool that finds all the phase shift groups. And then I found all the phase shift groups in this. Because I was making this slide and it has some bus numbers in there. What I did is I renumbered all the bus numbers so that these are not the actual bus numbers in the WCC case. They're just sequential values, so I could put it in the slide here. The algorithm that we use to do this is quite quick. For the 27,000 bus case, it took 6 milliseconds to do all the WCC. So now you've got a listing of the phase shift groups in your case. You can right click on them and see a dialog. We give you options to set all the phase shift groups to 0 if you don't want them. And we also give you an option to set the phase shift groups in your case based upon any modeled transformer vector groups. So applications of this, a lot of the applications just going to be for informational purposes. It's kind of nice to see these networks. It can help as we're doing the alternative solutions by helping us know what phase shifts to include as we're setting initial angles to do a solution or to set the initial angle on a new bus. Why we actually got into this is we were working on adding, we're working with EPRI on being able to export from PowerWorld the DSS files that are used by GitHarm to do harmonic analysis. And when you do harmonic analysis, you need to know the phase shifts that are actually there. So we're taking data that has the transformer vector groups in it, and then we're setting the phase shifts, taking advantage of the phase shift groups to set the correct OpenDSS initial values. Okay, so this is a summary. These things exist. We're not going to get rid of them because they're a characteristic of the power flow equations, which are modeling constant, or they're modeling power, which is nonlinear, and it's equal to V times I. And anytime you have power that's a product of two things, and you say the power is 0, you can have a 0 voltage or a 0 current. Or as it's not 0, it could be some combination of those. I've gone through options to avoid them. Research is ongoing to improve this. Some of the visuals that I showed you here are a result of new code that we've set up to help kind of quantify the impact of different solution options to see how they affect the region of attraction. So with that, if you're interested in papers, we have some of my, essentially all my recent papers are given there. That includes the NAPS paper that is going to be presented in October. So you can download them there. If you have questions, I can answer some questions right now, depending, I can answer questions right now, and hopefully Victoria will read what's in the chat, or you can email me later on. So thank you for participating. And Victoria, do we have any questions in the chat?
Actually, we do. We have 4 questions. So the first one says, does Helm end up at alternative solutions as well? And are there any similar techniques to get those sorts of cases solving by doing a series expansion on power flow equations, but perhaps not using copyrighted Helm method?
It's a what method?
HELM.
Yeah, in doing this, and I've been working in this area for a while, there are various methods that you can use. I'm not familiar with the details of that method, but there's different methods that you can use to solve the power flow equations. and what I would do in grad school is I would trace out these curves, and we do homotophic methods to trace things out. So that certainly can be used. The challenge you're dealing with is how much computation you have to uh, do to solve the equations. But I had code set up where I'd trace these curves around, and I was producing PV curves and QV curves and all different sorts of shapes, and I could go to all different alternative solutions. So
Okay. Our next question is, how do we know the operable solution if both the operable solution and the alternative solutions are having normal voltages of greater than 0.9, for example?
right, and that's where looking at the VDQ sensitivities can be very useful. So we've added that functionality. I mean, it's actually been in Power World for quite a while, but you do want to do that calculation. Again, the first thing I would do if somebody gave me a power flow case, I want to know is there an alternative solution there, is to find for the obvious ones, and the obvious ones are going to have low voltages. If we're using that, option where the constant power loads are reduced as the voltage goes down, it'll tend to have a low voltage or alternative solution near zero or at zero. That's the first check. But then if you want to check for the more difficult ones, and we're actually running into this as we do our geomagnetic disturbance analysis, because when you take a GMD and apply it to a power system, you're adding a lot of reactive power to it, and that is causing challenges with picking them up. But we do find this DVDQ sensitivity method does work, although you do have to be careful about the negative reactive branches. So we've added that check. One of the papers on the website, which I mentioned here, was work from one of my students where she was looking at, she actually presented a nice algorithm for figuring out whether a solution is alternative or not.
Okay, we have two more questions. This one is from Luke Kiernan. About operational equals stable. What does standard power system dynamics mean here?
We have a class here, 667, which Adam Birchfield is teaching this semester, and I've taught before, where we go through all the dynamics for the power system. But if you just put swing equation dynamics in there, you will tend to get negative. You will tend to get positive eigenvalues for these alternative solutions. The classic example that actually when I started doing this work in grad school, we were looking at energy methods, and energy methods are applied to power system dynamic analysis to assess stability. And you would have a energy well around what we call the stable equilibrium point. And on the boundary of the well, we would have unstable equilibrium points, UEPs. And even with just the swing equations, the eigenvalues on these, when you solve to one of these UEP solutions, which are the alternative power flow solutions, would indicate instability. And the ball in the well analogy is that at the bottom of a well, a ball, if you perturb it, it'll come to rest back at the bottom of the well. And on the boundary of the well, there are the saddle nodes where if you put a ball there, it'll stay there. It's an equilibrium point. But if you perturb it a little bit, it's going to roll away. And that perturbation, if you just model the swing equations on the generators, you will see this sort of behavior. But again, I just bring that up not because I think we should be looking at the stability of these values. If I had to say which solution do I want the solution that passes the DVDQ sensitivity test. that's how I would check for it. But if you read papers on this, you will see people referring to these as UEPs. So I just brought that up so that people are aware that it's being done. But having said that, the power flow in and of itself does not have dynamics associated with it.
Well, we are almost out of time. We do have one more question from Joseph Silvers. How do alternative solutions manifest in transient dynamic modeling? Presumably, you might see big changes in power flow state variables in a block start study, for example.
Joseph, nice to hear from you. He's a former student. Uh, in the stability realm, what's going to happen is you're going to start out at a stable equilibrium point. If you don't start at a stable equilibrium point, when you initialize your stability run, when you give it an initial perturbation, it's going to go off somewhere else. So you start from a stable equilibrium point, and then you give it a kick. It's sort of like you're taking the ball in the well analogy and you're giving that ball a kick. And if the kick is large enough, it's going to exit the well. Chances are it will not go through an unstable equilibrium point. So you will not see an unstable equilibrium point. You just won't end up there. And when I used to teach this at Illinois, sometimes I'd have a chair in the classroom, and I'd say, hey, if the chair is sitting on all four legs, it's stable. And if I hit it a little bit, it doesn't fall over. Then I'd try to balance the chair on like two legs or sometimes one leg if I was ambitious. And of course, I couldn't do it, but that would represent an unstable equilibrium point. If I kick that chair, and it's not necessarily going to go through that unstable equilibrium point.
All right, well, I think that's all of our questions. That's all of our time. Thank you, Dr. Overbye, for the insight on the power flow alternative solutions. And we'll be looking forward. Thank you, everyone, for participating today and for attending. And be looking for our upcoming webinars and events on the Smart Grid Center website at smartgridcenter.tamu.edu.
Thank you.
Thank you.
Thanks all. And if you have any questions, just send me an email there and I'll get back to you. Bye.